Hi, and welcome to Team 3, It's Always Sunny in Arizona's presentation video. First, let me introduce you to my team. I'm Stephanie Woodrow and have been the project manager for both semesters of this project. My primary functions are making sure our reports are turned in well and finished on time, conducting meetings for our team, and keeping the movement of the project flowing and cohesive throughout the semesters through the showcase. I live in Las Vegas, Nevada with my husband, who also happens to be one of the members of our team. Michael Payton started as our iOS coder and app designer, and as we've moved away from the app idea and individual coding for platforms, he has become our web server designer and coding specialist. Mike resides in Maryland and is our lone East Coast student. Satha Adawala started as our Android platform and app designer, and as we moved away from our app idea and individual coding platforms, she has become our second web server designing and coding specialist. She is our only on-campus student and unfortunately has to do all our presentations for us. Nicholas Emily is our hardware designer and circuit specialist and has designed our custom mountable boards for our project. He has worked to help implement our hardware and software designs together and conducted market research. Nick lives in Las Vegas with his wife, which is yours truly. Michael Krasner rounds out our team as our jack-of-all-trades specialist. He has been instrumental in our market research, backed up our hardware design team, and worked as our tech specialist for projects and assignments. Mike worked with Nick to provide a comprehensive market research survey to jumpstart our project. Our project was tasked with hacking an existing remote for sunshade control. What we have found throughout our project is that our team was able to create a more functional product at a fraction of the cost with a custom designed remote and web server that anyone can use to control their interior, exterior, vertical, and horizontal sunshades. In conjunction with our web server, we have added a simple Arduino board that can be added to any motorized sunshade control that will receive commands and do our functions for us. Using a 3D printer, we've made a custom PCB enclosure that can protect all of our components from exterior elements. Last semester, our team formed quickly into a 5-person team with direction and help from Professor Kazicki. We were able to quickly come together and define a structured outline of how to progress forward and brainstorm our ideas for this project. We began with a large market survey of both industries here in Las Vegas and talked to Professor Kazicki, who actually owns a sunshade. And in Las Vegas, we have 3 team members that are located there, and did a personal survey that we all took and asked friends, coworkers, and loved ones to fill out. And after completing our research, we had a good direction to head in. We worked to quickly decide what platform we would use to communicate our remote and hardware, and had initially settled on Bluetooth applications being the correct way to move forward. We did realize, though, that the range was limited and it made it less than desirable for our project in the long run, so we switched over to wireless applications. With this switch, we moved away from the idea of creating individual applications for both the iOS and the Android platforms and concluded that a web server was a simpler and more efficient setup for our design. Initially, we had settled on using the Arduino Nano BLE33 due to its Bluetooth capability. With the switch to wireless, we're no longer using that, and we are using the Arduino IoT to achieve our project goals. What started out as a block diagram and a simple schematic last semester for our hardware build is now a custom designed part that has been fabricated and ordered for our completed build, moving our project towards final completion. Our Gantt chart has major project outline with start times, length projections, and completion dates. Its simple structure has made it easy for our team to stay on track both semesters and keep our team from having much, if any, slippage at all in our actual schedule. Now, let me pass this over to Mike Krasner and let the experts show you our project.
Hi, my name is Michael Krasner, and I will be discussing the reasons why we moved from Bluetooth as a means of communication with the shade controller to Wi-Fi. I will also cover how we log in and connect via the controller web page. As you can see, the Bluetooth communication has a very limited range. Bluetooth 2 through 4 have only a range of 100 meters. Our first choices of Arduino microprocessor used Bluetooth 4.0 low energy, which could only reach that maximum of 100 meters. Testing proved that controlling the shade from a cell phone required the user to be in the same room and often very close to the controller. They would not go through walls, and going through different floors was absolutely a no. Statistics regarding the signal strength versus range will be discussed on another slide. Although Bluetooth 5 low energy has been available on most cell phones since late 2017, it is not as amazing as it first appears on this chart. For example, the 1,000 meter range is under perfect conditions in an open field and outdoors. The 400 meter range is using the long range mode, which lowers the maximum data rate to only 500 or as low as 125 kilobits per second and increases the current draw on the battery. The 2 megabits per second maximum data transfer rate is in a high speed mode, which further reduces the range. This chart shows the signal strength rating using RSSI, or the Received Signal Strength Indicator. Signal strength ratings go from 0 dB to negative 120, with 0 being the maximum. We see that starting at about negative 70 dB, the signal is okay, and anything lower only goes from bad to worse. This is a graph showing tests we ran from an iPhone on the Arduino using Bluetooth. We see that even at a distance of only 10 centimeters, the signal is rated as not good according to RSSI. At 30 centimeters, or just under 1 foot, it becomes unstable. While using Bluetooth to communicate with the shade, it did actually function in the room, but the obvious limitation was less than optimal for our project. Our only choice was to go from Bluetooth to Wi-Fi, increasing communication range and stability. Communicating with the microcontroller through Wi-Fi meant that we could now interface through a browser web page. Accessing a web page can be accomplished through anything that has an internet browser. First, the user will address their browser to 192.168.4.1. This will open the initial logon page where the user will input the network name and password. This information will then be saved in the Arduino and should not need to have been re-entered unless the Arduino is without power for an extended period or the board itself is cleared. After the information is submitted, the user then clicks the reset button, which power cycles the Arduino. Finally, the user will open the address http://ASA controller, which will grant them access to the controller GUI page. After pointing to this new page, this will open the general user interface where the user can click buttons to raise and lower the shade. The user can also set automated control settings based on temperatures. Here's a basic flow chart of the steps. You can see that the user powers on the device for the first time, points to the IP, inputs all their information, clicks the reset, which saves the information, points the browser to the ASA controller, and now the sunshade controller web page is there, and the user can then raise and lower the shade via Wi-Fi and set points such as temperature to deploy and retract. Thank you for your time.
Hello everyone, my name is Safa Awadallah and I'll be talking about the Arduino. The original proposal was to use the Arduino Nano 33BLE Sense card, which had several of the sensors to monitor sunlight. However, integration testing revealed that the Bluetooth range was under ideal. Instead of the Bluetooth technology, we have decided to use Wi-Fi connectivity, which provided better user interface, reduced cost, and improved operation range. Since making the shift to the new microcontroller, we have been able to communicate from a web browser to our custom web server on the Arduino Nano 33 IoT. Let's take a look at the code. In the void setup section here, we're setting up the analog resolution at 12 bits, as well as initializing the Wi-Fi chip. In this section over here, we're checking to see if there's a network configuration, otherwise we'll just create an open network. In this section over here, we're reading the wind sensor as well as checking the Wi-Fi status. Over here, we're checking to see if it's safe to automate. If wind levels has not broken 5 miles per hour for 30 minutes, then it is considered safe. In this section, the isolated server method is being used to serve a website before the user's network parameters have been loaded to the Arduino's flash memory. This allows the users to enter their network credentials for the Arduino to store. In this section over here, we're able to get the wind and temperature data from the device sensor. Wind is measured in miles per hour, while temperature is measured in Celsius. In this section over here, we are returning the averages of the values based off of an array of 5 values. Over here, we're sending a command to raise the shade, and over here, we're sending a command to lower the shades. Lastly, we're allowing users to indicate if they want the shades to work in automated mode, if it is safe to do so. Thank you.
Hello, my name is Michael Payton. I'm going to be giving you a quick rundown of the initial circuit board, enclosure, and light sensor prototyping we have conducted this semester. Last semester, we conducted most of our prototyping on breadboards. This allowed us to quickly swap out parts and test several different microcontrollers, among other things. This semester, we continued prototyping using breadboards until we had successfully identified the components that we felt would give us the best performance. Some of the prototyping conducted this semester includes playing with the idea of adding an LCD screen, adjusting the transistor model, and conducting testing on a light sensor. I'll provide more detail about the light sensor in a later slide. Having identified the correct parts, we moved the components to a more permanent solder breadboard, our initial prototype board shown here. One of the benefits of moving the components to a soldered breadboard was reducing the footprint. It also fixed the components in a position that allowed us to develop our first prototype case. To produce this case, we turned to 3D printing technology. I'm sure many of you have been exposed to 3D printers, but for those of you who have not, this is how the process worked for us. First, we created a model of the board using a free software called Blender. Then we exported this model to another free software called Cura. This is a slicing tool that develops a G-code file that a 3D printer can read. Finally, once the G-code file was created, we fed that to the 3D printer and it got to work. Now to the light sensor prototyping. We created a light sensor circuit using a photoresistor to vary the voltage that was sensed on one of the analog pins of the Arduino. We then used a light meter and a light source set at a fixed distance from the photoresistor and the light meter so that both would receive the same amount of light. Finally, we varied the light levels and recorded the readings of both the light meter and the analog pin of the Arduino. We compiled this data and generated the graph, trend line, and formula you see here. Using this formula, we're able to accurately predict the amount of lux hitting the photoresistor, plus or minus 2 lux from 0 to 400 lux, and plus or minus 10 lux from 400 to 600 lux. We feel like this should give us the ability to sense whenever it's dawn and dusk outside, and then deploy the sunshade accordingly. Now I'm going to pass you over to Nicholas Imlay, and he's going to talk about the next really exciting stage of our project, creating a custom printed circuit board. Thank you.
Hi, my name is Nick Imlay, and I was responsible for the hardware aspect of our design of our sunshade automated system. And for this design, we wanted to build a complete custom circuit board, and in that process, we ran across some software issues in relation to the schematic and board layout softwares that we were attempting to use. And the first software that we were using would not allow us to create new schematic symbols that did not exist in the provided library. The second software would not allow us to place the parts that were needed to create the footprint for the component less than 25 mils apart. And at this point, we're running into a time limit to be able to have our simple board made for our demonstration day. And so what we decided to do was go ahead and create a simple board design that would allow us to cleanly attach our prototyping boards together and the other various discrete components that we were using. For the demonstration day, we are going to be creating a video demonstrating the functionality of our automated sun system, in which we show that the use of our temperature sensor, as well as our wind sensor and our light sensor, and then our automation based on forecasted weather, based on wind, and then the manual shade movement, and also the automation based off of temperature and light. For this presentation, Stephanie introduced our team and provided a brief overview of our project. Mike Krasner discussed some statistics in regards to the use of Bluetooth versus Wi-Fi, and an overview of our graphical user interface. Safa provided some insight into the coding changes that were required to change our system from Bluetooth to Wi-Fi, and how this allowed our us to switch from an app to a GUI where the user only would need the IP address of their system to access the user interface. And then Mike Payton shared about the prototyping and fabricating of an enclosure that he has done for our team project. Thanks. Have a great day.